Okay, and I think now time is already,
Yeah, it's 3 p.m.
yes, 3 exactly. Yes, so let's start. So I welcome everybody to our 15th lecture of our astrochemistry lecture course. And this lecture will be given by Dr. Alessandro Morbidelli for Côte d'Azur Observatory in France, which is in Nice.
Yeah, actually, just
And
changed my affiliation. That's why I modified that. So
okay,
I
maybe then
actually,
you,
I now
okay,
professor at Collège de France in Paris, but I share my time between Paris and Nice. So
I see. Okay. Okay, so he will speak about origin of the solar system. So Alessandra, please, the floor is yours.
okay, thank you very much. Thank you for the invitation. So we try in these 2 hours, a little bit less, to give you an overview of the origin of the solar system, without going too much in the detail, but trying to cover the whole ground. So there is a lot to say. So we'll not go too much in depth, of course. So let's start with a global presentation of the solar system. Of course, the solar system is made first of all by its planets. There are 8 planets in the solar system, and they are divided in 2 categories because of their physical properties. You have the 4 terrestrial planets in the inner part, from Mercury, Venus, Earth, and Mars. And these are planets which are essentially rocky. The Earth is the major one. Venus almost has the size of Earth, and Mars and Mercury are much smaller, a tenth or 20th of the mass of Earth. So they are rocky. They have, of course, some have an atmosphere. Earth and Venus have an atmosphere, but in terms of mass, it's totally negligible. When we go further away, much further from the sun, at beyond 5 astronomical units, so 5 times the Earth-Sun distance, we have the 4 giant planets. And these giant planets are giants by mass, because they go from 300 Earth masses for Jupiter to 15, 17 for Uranus and Neptune, but they also have a different physical nature. In fact, themselves, the giant planets can be divided into gas giants, which are Jupiter and Saturn, for which most of the mass is due to hydrogen and helium, so the same elements that compose the sun. For instance, Jupiter, 300 Earth masses, about 260 Earth masses of hydrogen and helium, and only 40 are in what are called metals or heavier elements. And then we have the so-called ice giants, and they're called like that because of their 15, 17 Earth masses. Hydrogen and helium only account for a couple of Earth masses of material. We don't know exactly how much, but most of the mass should be in heavy elements and presumably in a core made of rock and ice, and that's why they are called ice giants. But we don't really know much about their interior structure because they've only been seen in quick flybys by the Voyager missions. And that's why one of the goals of the US Decadal Survey, but also Europe Voyage 2050, is to go around either Uranus or Neptune, most likely Uranus, in orbit in order to measure the gravitational field of the planet and deduce really precisely the internal structure of these planets, for which we don't know very much. So in terms of planets, the inventory of the solar system is complete. Maybe I put a question mark because, there is some discussion about the possibility of a 9th planet that would be very far out, something like 700 astronomical units, 700 times the distance between the sun and Earth. It's not seen, this planet. It is deduced by looking at the perturbations of some part of the Kuiper belt that I will discuss in a second. But there is some debate. So even there, whether there is really something to explain or not, depending if one accounts for all the observational biases or not. So it's quite debatable. So we might not even have a complete inventory of the planets in the solar system, but apart from this rogue planet, certainly the rest of the planets are known. So in terms of chronology, the fact that the giant planets contain hydrogen and helium immediately tells us some information about when these planets formed, because these planets must have formed before that the gas leaves the protoplanetary disk. So before a few million years, because typically the lifetime of a protoplanetary disk is only a few million years. So all the giant planets must have completed their accretion in just a few million years. The orbits of the planets, both terrestrial and giants, are almost circular and almost coplanar, which we thought was trivial thing because planets form in a disk. But then when we compare with extrasolar planetary systems, we see that having circular and coplanar orbits is quite peculiar of our own system. In addition to the planets, our solar system is characterized by populations of small bodies. And so we, first of all, we have no bodies, stable bodies at least known, between the Sun and Mercury, and they've been searched quite actively in transit over the Sun, and nothing has ever been discovered, which is significant today because we know that so many extrasolar planetary systems have material, even planets, much closer to their star than Mercury is to the Sun. And we don't have any planets so close to the Sun, but not even small bodies. So this is really a peculiarity of our solar system. And the first reservoir of small bodies is the asteroid belt, which is confined between Mars and Jupiter, in a belt there. So the asteroid belt is made of a large number of objects of various sizes. It goes from Ceres, the biggest of the objects, which is 900 kilometers in diameter. There is about 1 million objects bigger than 1 kilometer, and more for smaller objects. But asteroids are not the only reservoir of small bodies. We have also the Trojans of Jupiter and Neptune. So these are objects, asteroid-like, that are on the same orbits of these two planets and are around the Lagrange points. So they precede or trail Jupiter or Neptune by 60 degrees. And in addition to the Trojans, there are also satellites around all the giant planets. There is a system of regular satellites. These are satellites that orbit the planet on the equatorial plane, even if the planet is inclined in the same direction of the rotation of the planet, as one would expect from formation from a circumplanetary disk. This is why these are called regular satellites. But there are also irregular satellites, and these are satellites on a more distant with respect to the planet than the regular satellites. They can have very eccentric orbits and very inclined orbits, and about 50% of them even retrograde orbits with respect to the rotation of the planet. This is why I represented them with these inclined arrows. And they've been first discovered around Jupiter, but eventually they've been discovered around all giant planets. If we zoom out a little bit, so we focus all the planets in the first 30 AUs in the left part of the plot, and we go to a logarithmic scale, we see that the solar system is much more extended than the planetary system. So we have the Kuiper belt between 40 and 50 AU. This is a sort of analog of the asteroid belt, but is made of objects that are rich in ice, and not only water ice, but also some other ices like ammonia or nitrogen or CO and so on. The biggest objects in the Kuiper belt are about 2,500 kilometers in size, like Pluto or Eris. And then, of course, there is a size distribution as for the asteroid belt. And the Kuiper belt has a peculiar structure. So there is between 40 and 50 AU, there are objects that have quasi-circular orbits. They can be quite inclined, up to 40 degrees, but they are confined in the 40-50 AU region. But then there is an extension that we call, sometimes it's considered part of this Kuiper belt, but sometimes not. It's called the scatter disk. These are objects that have large eccentricities. And so at perihelion, they come close to Neptune, so they feel gravitational encounters with Neptune. This is why it's called scatter disk, because these orbits are not stable. Due to the effect of close encounters with Neptune, these orbits continuously change in some major axes and eccentricity. And in general, these orbits are very eccentric. So at aphelion, these bodies can go even up to 1,000 astronomical units. And these are those which seem to have an uneven distribution along the ecliptic, and for which so the existence of a putative 9th planet around 700 AU is invoked in some works. And the scattered disk is the origin of short period comets. And at the extreme of the scattered disk, we have the Oort cloud. The Oort cloud is another reservoir of comets, but it's so far out that it's disturbed by the galactic potential, the passage of nearby stars. And so there, instead of having orbits which are relatively confined on the plane, around the plane of the solar system, inclined by a few tens of degrees, like the regular satellites, we can have all kinds of orbits, half of which are retrograde with respect to the motion of the planets around the sun. So the scattered disk is the bridge that connects the Kuiper belt to the Oort cloud. The Oort cloud is today the source of the long period comets. And if you see, so the solar system has the same structure that we see for the satellites around the giant planets. So close in, you have the regular bodies like the planets that turn around the sun all in the same direction. And then further away, you get these strange orbits, which can be eccentric and retrograde. And it's the same for the satellite. Close to the planets, you have the regular satellites. Far away from the planets, you have the irregular satellites, which are really the analog of the Oort cloud for the sun. So these are the reservoirs of small bodies. And of course, sometimes small bodies escape from these reservoirs and become objects that are transient, so that for which we see populations, but these populations are in steady state because objects are quickly removed. And so if we see these objects, it's because new objects come and substitute the objects which are removed because they are unstable. So basically, they are the near-Earth asteroids. These are asteroids escaping from the asteroid belt and crossing the orbits of the terrestrial planets, but also the comets, and they mentioned before, the short period comets coming from the scattered disk and the long period comets coming from the Oort cloud. And before these comets become visible, while they cross the giant planet region, they are called centaurs. So asteroids are studied, of course, using telescopes, now with space missions. But what we know most of asteroids is due to the fact that some fragment of asteroids can be destabilized, can reach the Earth, fall on Earth, and be studied as meteorites. So meteorites give us a lot of information on asteroids, and so a lot of information on the origin of the solar system. So first of all, there is a category of meteorites that are called chondrites. These are meteorites that never heated up and so enough to melt. And so we can really see what are the constituents of these asteroids, of these planetesimals. And they are little spherules called chondrules, some grains called much smaller in size, that called matrix, which cement all these chondrules together. And then these strange grains, white grains, inclusions that you see here and there, which is called the calcium aluminum inclusions, because they are mostly made of calcium and aluminum. And calcium and aluminum are the most refractory elements. So these are the elements that should condense first from a hot gas when the temperature decreases for the first time below 1400 degrees, 1400 degrees. I hope you see my mouse, right? It's here. Okay, so these are the first minerals that condense from a hot gas around the sun. And these minerals can be dated using radioactive isotopes like the uranium-lead system. And so they are dated now with great precision. So they formed 4,568,000,000 years ago. And just the last digit is disputed. So it could be 68 or 67. Now, many people think it's more 68. So that's the date at which the oldest minerals ever recorded in meteorites formed. So it's considered to be the time zero of the solar system. People ask you, how old is the solar system? Well, it depends, of course, what you look at. But the oldest minerals is 4,568,000,000 years ago. So it's time zero. When you then see the chronology, like Mars forms in 5 million years, Earth, Moon forms in 100 million years, it's relative to this date. Now, what is this date corresponding to in astrophysical terms? Okay, it's the date at which the first solids form, but how is the system at that time? And this is not clear. So what time actually CI is formed in the timeline of stellar formation and evolution? So you've probably seen in other lectures that when stars form, they're first embedded in a spherical cloud. It's called class 0. Then these spherical clouds start to be punctured at the poles because the jet of the star is called class 1. And then the envelope disappears and remains just the star and the disk. That's called class 2. So when exactly the temperatures start to decrease below 1400 Kelvin, it's not so clear. It's probably in the transition between class 0 and class 1, but we're not so sure. The analysis of these calcium aluminum inclusions, also called the CAIs, show that when these mineral formed, there was a significant amount of aluminum 26. Aluminum 26 is an element which is unstable and decays on a short time scale of only 700,000 years. And it is computed that the decay of aluminum 26, which releases, of course, energy like core radioactive decay, was the most important source of energy of planetesimals. So a planetesimals that forms very quickly after the formation of CIs would have quite a lot of aluminum 26, and its decay would increase the temperature of the planetesimals enough to melt it, whereas planetesimals that form relatively late, they, of course, aluminum 26 would have already decayed before the formation of the object, and so this source of energy would be less, and the body would heat much less. What I just said is illustrated in this plot. This plot shows, as a function of the time at which a planetesimal forms, time 0 being the time at which CAI is formed, and the size of the body, the maximum temperature that the body reaches because of the decay of aluminum 26. As you can see, if the body is very small, just a few kilometers, it remains cold because, of course, heat is very effectively irradiated away, and so the body never accumulates a lot of energy. But as soon as the body is a few tens of kilometers, you see that this plot, the colors are vertical bands. So that means that the maximum temperature that the body reaches is basically independent of its size. And any body that forms before 1.3 million years or so reach a temperature of about 2000 Kelvin. So that's a temperature at which all silicates melt, and which means that a planetesimal cannot remain pristine. Everything has to melt. And once you melt your planetesimal, then of course all the minerals change. And you can also have the segregation of iron, which is the heavier of the elements, towards the center, forming a core, whereas silicates, which are lighter, stay around it in a mantle. And so that's the process of core mantle differentiation of objects. Objects that are formed after 1.3 million years, 1.5 million years, still can heat significantly. You see 1,400 degrees, then you go into the blue, it's still 1,000 degrees and so on. But this temperature is not enough to melt silicate. So these bodies can be altered by this high temperature. For instance, if there is water is liquefied, and then you can have water alteration, but you don't have iron silicate differentiation, and you can preserve the original grains like chondrules and CIs. What is interesting is that when we look at the meteorites, we actually have samples from both categories of objects. We have samples from objects that heated up and melted, and samples from objects that did not heat up enough to melt. And indeed, these are called differentiated meteorites, meteorites that come from bodies which melted, and undifferentiated meteorites or chondrites, which come from bodies that did not reach a temperature high enough to melt. And so among the differentiated meteorites, you have, of course, the iron meteorites that come from the iron core of a differentiated planetesimals, but you can also have chondrite meteorites coming from the crust or from the mantle of these bodies. And for some of these differentiated meteorites, we know the parent bodies. So first we have meteorites from planets like Mars or the Moon. Then some meteorites have been identified with asteroid Vesta. Some meteorites, the oblates, have been identified with E-type asteroids in the Hungaria region, and so on. The parent bodies of iron meteorites are not so well known, and there is a space mission visiting asteroid Psyche in order to try to understand better the link between asteroids and these iron meteorites. Chondrites, on the other hand, so are not differentiated. They heated up, but not enough. So we still see the pristine structure with the CIs, the chondrules, as I showed before. We have basically two big categories of chondrites: carbonaceous chondrites that contain a significant amount of carbon because they have a lot of matrix, and then ordinary chondrites or enstatite chondrites that have a much less matrix. It's basically just an accumulation of chondrules sticking together. And C-type carbonaceous chondrites are typically related to C-type asteroids, and ordinary chondrites to S-type asteroids, and enstatite chondrites to X-type asteroids, as are classified using spectroscopy. So the fact that we have these two categories of meteorites immediately tells us that the solar system had two, at least in the asteroid belt, or what ended up in the asteroid belt, had two generations of planetesimals. Right? There are planetesimals that formed early in the first 1.5 million years, because this is the limit time to have enough aluminum-26 to melt. And then we have planetesimals that form later. So planetesimal formation was not just a snap, when you at a given time you form all the planetesimals. Is a protracted process that covers millions of years. And the last of the chondrites probably formed at 3-4 million years after CAIs. What is not known if we have a continuous process of planetesimal formation ranging from the first million year to the end of the disk, or we have two episodes of formation. So a first episode of early planetesimal formation, then a sort of gap during which not much objects formed, and then again planetesimal formation at the later times, maybe close to gas removal. It's not so clear because, well, we have some dates and, but it's not so clear if there is a real gap, if this gap, there is an apparent gap indeed, but it's not so clear if it is due to sampling biases or not. So keep this in mind. So this concerns the chronology of planetesimals. So planetesimals started to form very early in the first million year, but we have also planetesimals forming after 3-4 million years towards the end of the disk lifetime. This is for asteroids, because asteroids sends meteorites to us, but we have an indication that also Kuiper belt objects formed, or at least some of them, form very late. Of course, we don't have meteorites from Kuiper belt objects, but we have some indication of their density. And their density is measured when we know the size and the mass. So the size is deduced from observations, because you measure the luminosity in the visible, in the infrared, so you can get an estimate of the albedo, and this allows you to determine the size. The mass is more difficult, but luckily many KBOs, Kuiper belt objects, have satellites, and when you have satellites, then you can measure the mass. And so you can determine the density. And as you can see, there are objects, or for small objects, where the error bar on the density is huge, but there are objects for which the error bar is not so big, and the bodies are big, up to 700 kilometers in size, and their density is less than 1, the density of water. So these objects should not be differentiated. It's quite inconceivable that a planetesimal differentiates, the water melts and then it freezes again, and still you have a porosity which is very high to have a density less than 1. This is really inconceivable. So these must be planetesimals made of rock and ice, which remain very porous because they never heated up and the ice never melted. And to not to melt ice means that the temperature never exceeded 200 degrees or so. And so clearly these bodies should have formed very late in order to have very little amount of radioactive elements. Otherwise, water would have melted. Then, of course, the bigger KBOs like Pluto, Eris, Quaoar, and so on, they have a higher density. They are probably at least partially differentiated, but then, of course, it's their gravity, the gravitational accumulation releases energy, and this is enough to melt these bodies, even if they formed later. So, but we don't know about these, but these ones, intermediate ones, certainly should have formed very late. Very late means around 4 million years after CIs, that is enough. So this is for the small bodies. What do you know? Do we know about planets? So I already said at the beginning that the giant planets must have completed their formation before disappearance of the protoplanetary disk, so before 4 or 5 million years. The terrestrial planets don't have any hydrogen and helium, so we cannot use capture of hydrogen and helium as a chronometer, but we can luckily date their differentiation into a iron core and a silicate mantle using some radioactive chronometers like the hafnium tungsten system. I don't have really time to explain how it works, but it's a way to date how fast the metal, the iron, was segregated in the core of the planet. So for Mars, the result is what is shown here, and from this paper by Dauphas and Pourmont, and it shows the yellow envelope, the possible growth history of Mars, growing from 0 mass to its final mass as a function of time, again 0 being the CAI formation times 4.56768 billion years ago. And so as you can see, Mars should have completed its formation again in 5-6 million years, so forming very quickly. Essentially Mars stopped forming on the same time scale of the giant planets, on the same time scale of the latest of the planetesimals that formed in the asteroid belt. For the Earth, the situation is different. So we can use the same chronometer, and then we can say, okay, if the Earth accretes small bodies one after the other and continuously differentiates into a raw, as soon as it accumulates iron, the iron melts and goes into the core, and the silicate remains in the mantle. We can use the hafnium tungsten chronometer to put some limits on when the Earth reached the 63% of their mass or 90% of their mass. There is some uncertainty, which depends on how much the iron equilibrates with the mantle before going into the core of the Earth. It's supposed to be somewhere in between 50% and 100%. So depending on how much it is, you see the Earth reached 63% of its mass between something like 12 million years and 25 million years, and reached 90% of its mass between 25 million years and 55 million years. But of course, this is assuming that the Earth just accreted small bodies continuously and continuously formed its core. And we know that this is not true because we have a beautiful moon. The moon is the outcome of a giant impact that ejected enough material in orbit around the Earth to form a circumplanetary debris disk out of which the moon formed. And to form such a disk, the Earth must have suffered a collision with another protoplanet, probably the mass of Mars, of a few times the mass of Mars. So clearly it's not really this schema, right? And in principle, if during the moon forming event, the core of this protoplanet impacting Earth had equilibrated completely with the entire mantle of the Earth, then essentially the Earth could have formed in one day, and what is enough is that the moon forms late enough. But simulations of this process of giant impacts tend to show that the core of the impactor does not equilibrate very well with the mantle of the target, because basically the two cores merge and then the two mantles merge, and there is not much iron silicate equilibration during giant impact. So probably this chronometer still tells us that the Earth formed in several tens of millions of years before the last giant impact that produced the moon. We can try to date the moon itself, so the last giant impact that formed Earth. There again, you can use many chronometers depending if you want to see when the moon differentiated, crystallized, its crust formed, and so on and so forth. And all these chronometers tend to give different ages that can be interpreted differently. So there is not a unique consensus on the age of the moon. You can find estimates ranging from 50 million years to 150 million years after CAIs. So it's a big factor of free uncertainty, which is quite embarrassing. But in any case, it's relatively late. So we're not talking a few million years like Mars or the chondrites or the giant planets. We are talking at least an order of magnitude more, at least 50 million years. So the Earth took much longer to form, and in particular, this giant impact which ended the formation of Earth and produced the moon did not occur close to the disappearance of the disk, but occurred much later. So this is my first half an hour, and I think I gave you a very quick presentation of the solar system, its structure in terms of planets and small bodies, and also the main constraints that we have in terms of chronology, thanks to the analysis of meteorites, but also other considerations like existence of hydrogen in the atmospheres of the giant planets, density of KBOs, and analysis of core mantle differentiation in the moon and the terrestrial planets. Now I will go into the second part of my lecture, where I will describe what are the major steps towards the formation of planets and towards the formation of the solar system. So basically, if you want to form planets in general, there are two main steps that we need to consider. The first one is converts dust into planetesimals, and the second step will convert somehow planetesimals into planets. So let's start from the first one. So when the star forms, it's surrounded by a circumplanetary disk. This was a theoretical prediction at the time of Laplace. It's now an observational fact, because when we look at young stars, we see that all young stars are surrounded by a disk. And then the number of stars surrounded by a disk declines with the age of the star. And typically after 2-3 million years, only 50% of the stars still have a disk. And after 10 million years, only a few percent of the stars still have a disk. By the way, did not mention that, but the meteorites also record the duration of the lifetime of the disk around the sun, because when there is a disk, there is a magnetic field associated to the disk, and some minerals record the magnetic field. And what we see in meteorites is that minerals that crystallized, became cold before 4 million years record the magnetic field associated to the disk, but minerals that cooled after 5 million years don't record any magnetic field. And so this is considered as evidence that the disk around the sun disappeared between 4 and 5 million years, which is perfectly in line with what we see statistically around other stars. So the disk is made of gas and made of dust. The dust is initially small, but the dust can stick together due to electrostatic forces and grow a little bit. And as dust grows, there are two movements which characterize the dynamics of the dust. One is the sedimentation towards the mid-plane. So the dust, the grown up dust, tends to be more concentrated around the mid-plane of the disk than the gas itself. And this is observed when you look at the extrasolar disks and you look at micrometer dust in scattered light. You see that the dust is distributed vertically as much as the gas. But when you look at millimeter-sized dust, for instance, with ALMA, you see that the dust disks are really a razor thin. So sedimentation is the first dynamical process that characterizes the dust. And the second process is the radial drift. This is due to the fact that the gas orbits around the star a little bit more slowly than the Keplerian motion. And this is due to the fact that the gas feels a pressure, because there is higher density of gas closer to the star than outside. There is a pressure gradient inside out, which subtracts a little bit from the gravitational force of the star. And so to be on orbit around the sun, the gas has to have a little bit smaller centrifugal force, so a little bit slower orbital velocity. So the dust tends to orbit at the Keplerian velocity, so feels a headwind from the gas. And so it's like when you bike and the wind is slowing you down, the dust is slowed down by the gas. And if you slow something in orbit, then it spirals towards the central star, and the orbital radius shrinks. And so you have this net drift towards the star. This drift is very slow for tiny dust, because it's very coupled with the gas. So it tends to be in orbit around the star at the same speed as the gas. Tend to be very small for large planetesimals, for instance, a million of centimeters, because of course they are big. The friction with the gas becomes negligible, but can be very strong if you have a size of about a meter, for instance, and then you can have drift speeds which are very large. For instance, in the Kuiper belt, the first astronomical unit, something like many thousands of centimeters per second. So this is 50 meters per second, which is a lot. It's really a fast drift. So the grains, as I was saying, hit each other, can stick by electrostatic forces, form fractal aggregates that then they self can stick and become more compact. But if aggregates come together with enough energy, they start to lose pieces or they destroy completely. So there is a limit how big grains can grow by electrostatic forces. Of course, there is no gravity here. The grains are still very small. And of course, it depends on the mass and the velocity, because it depends on the collisional speed, collisional energy. So the velocities are given by the radial drift of the grains, because the grains drift towards the sun, but these drift velocities are size dependent. So two grains or two aggregates of different size will drift towards the sun at different speeds. And so when they collide, they will have a relative speed, which is not negligible and can be computed. And then there is also some velocity, relative velocity, due to the turbulence in the disk, that for which we don't, it's difficult to estimate. So one can give some educated guess on how much the velocity dispersion to the turbulence can be. When you use these estimates for the velocity, so the drift velocity and the dispersion velocity due to turbulence, and you use the laboratory experiments to see how big grains can grow, the result is that for silicate, so if your monomers are silicate grains, then grains, aggregates can grow up to a size of about millimeter, and then they start to bounce off each other or lose chips. And if the grains, the monomers are contain ice, then the grains become more sticky. And this is not difficult to understand. Everybody plays snowballs on the mountains, but nobody plays sand balls on the beach unless you put a lot of water in your sand. That's really because water has sticking properties much better than rocks. In that case, so you can form aggregates, maybe a centimeter, maybe a decimeter in size, that some people call pebbles. Okay. So this is what combination of theory and experiment seems to suggest, is that just by sticking grain, you cannot form a planetesimal, you cannot form a comet, you cannot form an asteroid. You can only form grains that can, depending on their physical properties, range from a millimeter in size to a few centimeters in size. So this is what theory says, but is this correct, or is just a limitation of our understanding? Well, when we look at these meteorites, the meteorite that did not melt, so they did not differentiate, we can really see what meteorites are made of. And they are really made of these grains, the chondrules, right, and some CIs that are typically of a millimeter in size, or a fraction of a millimeter in size. So the idea that grains can only grow up to a limit size, which is small, is probably true. And then what happens is that all these grains, all these millimeter chondrules, or have somehow to come together and form a big object. And how can they do it, given that they cannot stick one by one? The idea is that there are instabilities that in hydrodynamical instabilities that allow all these particles that initially are dispersed in the disk to clump together and in some cases clump with a density which is high enough that these clumps become self-gravitating, and then all these spherules are bound by their common gravity and they can only contract to form a planetesimal. So how can we form these clumps? There are two instabilities that are produced in the disk made of gas and particles. And one of these instability is related to the sedimentation towards the midplane. It's called the Kelvin-Helmholtz instability. And the other instability is due to the radial drift of the particles towards the sun, and it's called the streaming instability. And I put here some seminar reference for these processes. This movie here that I'm going to play is an animation of what happens during sedimentation on the midplane. It's a little bit easier to understand. So what you see here is a cut in the disk at the given distance from the sun. So this is the vertical direction and 0 is the midplane. And the x-axis is the azimuthal direction around the sun. The colors show the density of the dust, okay? And the time of the movie is illustrated here. So what we are going to see is that with the movie running is that the dust will try to settle on the midplane. So its density will increase. The colors will go from blue to yellow to red to yellow as density is increased. But as the density of the particles of the midplane increases, there is an instability, the Kelvin-Helmholtz instability that develops, producing turbulence. And so let's see what happens. So start the movie, you see this band becomes narrower with sedimentation, density increases, and here the turbulence kicks in. So the band cannot become indefinitely thin with an infinite density. The particles remain dispersed on the band. But now, because the disk has become turbulent, the particles tend to be trapped in vortices. And so instead of having a band of dust with a uniform density, you see that the dust can be trapped in vortices and then form high-density clumps of particles. Under some conditions, some high-density clumps like these ones can reach self-gravity, density high enough for self-gravity to kick in, and then the clump is held together by the common gravity. So this is what happens during sedimentation. During radial drift, it's about the same. If you have initially dust and gas, the dust drifts towards the sun, and then even if the dust is initially uniformly distributed on the midplane relative to the gas, you can start to see the formation of filaments. So what are we seeing here? 3 snapshots at 3 different times. The colors show the density of dust compared to the initial uniform density in logarithmic scale. This is a plot before we were seeing the disk in the vertical direction at the given distance from the sun. This now we are seeing from the top, the midplane. So this is the radial direction away from the star, and this is the azimuthal direction. We are on the midplane now. And so we don't see the vertical direction. So initially you can see that the dust is not uniform. There are some blue patches and green filaments. So this is the beginning of the streaming instability. Then this instability develops, so you have more and more defined filaments, and the filaments start to break in clumps. And then some of the clumps become so pronounced that the self-gravity of the pebbles, of the particles, keep all these particles together. And when a clump reaches self-gravity, it's circled by a white circle to highlight it. So as you can see, you start from a uniform density of dust, and then you have the dust tends to clump, and you get a large number of self-gravitating clumps that will contract and form planetesimals. So this is how we think macroscopic planetesimals of kilometers in size can form. And actually, a very interesting work by Huber-Clark and Schreiber show that typically the size of the planetesimals formed by this self-gravitating clump is about 100 kilometers in size. Why 100 kilometers? Because it's very rare to form a super clump, of course. It can happen, but it's very rare. This is conceivable. It's easier to form small clumps, but big clumps. But small clumps don't have much gravity. So even if they are self-gravitating, their contraction is very slow. And these clumps tend to be dispersed by turbulence, tend to shear out, tend to have mutual encounters. So typically, small clumps are destroyed before they can actually contract and form a planetesimal. So the optimum is about to have enough mass in these clumps to form relatively frequently and be sufficient resilient to survive during the contraction time scale and form a planetesimal. And this leads to planetesimals of typically 100 kilometers in size. The contraction of the particle cloud, it's interesting because particle clouds in general will have a rotation because they are in the disk, and the disk is in differential rotation, so the particle clouds are in rotation. And so if you have a rotation, you have an angular momentum. And so clearly not all particles can collapse to the center, because where does the angular momentum go? So conservation of angular momentum tells you that these particles, as they collide, as they contract, they don't form a unique body. They tend to form several bodies, some of which are left unbound, but typically they form a binary. Okay, so this way the particles solve the angular momentum problem is to form a binary, which is a little bit like stars. Most stars form like binary because of the same reason. Then maybe these binaries, by mutual collisions or mutual close encounters, can dissociate later. But at the beginning, all planetesimals should be born as binaries, and binaries of roughly equal size, as you can see here. What is interesting is that not in the asteroid belt, but in the Kuiper belt, we do see binaries like these ones. And we think that this is because the asteroid belt was very perturbed during planet formation, and is sandwiched between Mars and Jupiter. But the far end of the Kuiper belt, what is called the cold Kuiper belt, was far enough from all planets not to be very disturbed and never contain much mass. So the binaries that formed remained as binaries. And indeed, 50% of the objects that we see in the distant Kuiper belt are binaries. And these plots here show the properties of the real binaries in triangles in terms of the magnitude of the primary, so which is related to the size, and the difference in magnitude between primary and secondary, which gives you a sense of the mass ratio. So these are almost equal size binaries. And the blue and green dots are what are predicted by simulations like the one I showed you, starting from the clump produced during the streaming instability and then simulating the collapse of these clumps to see what kind of binaries are produced. The same is true for 7 major axes versus eccentricity, the orbit of the binary. The triangles are the observations, and the colored dots are what is produced in simulations. So as you can see, simulations reproduce quite well the properties of the binaries that are observed in the Kuiper belt. And on top of that, they are able to reproduce the orientation. So when you look at the binaries in the Kuiper belt, some of them are prograde, some of them are retrograde, some of them are inclined. And so the cumulative distribution of the inclination of the binaries that are observed is this dashed curve. So as you can see, there are a variety of inclinations. It's a cumulative distribution as a function of the inclination. And there are a variety of inclination. 80% of the binaries are prograde and 20% are retrograde. And it's very difficult to reproduce this 80-20% ratio. There have been many models, including from outstanding scientists like Peter Goldrake, and failed completely. And the model of collapse of these clumps generated in the streaming instability for the first time reproduces this 80-20 ratio. And this is the statistics given by the solid curve. So this is considered to be really the orientation of the orbits of the binaries are considered to be a proof of the fact that planetesimals form in the streaming instability. So problem solved? Yes and no, because both instabilities, this Kelvin-Helmholtz instability and the streaming instability, manage to create these self-gravitating clumps only when the ratio, the density ratio of dust over gas on the midplane exceeds unity. And typically, starting from the solar metallicity, so the initial dust to gas ratio, the material that composes the sun and the circumsolar disk, it's difficult to conceive that on the midplane, the dust to gas ratio is larger than unity everywhere, even if one accounts for sedimentation. So the idea is that the conditions for our current understanding is that the conditions to form self-gravitating clumps of pebbles are not united in general. And in order to be able to form these self-gravitating clumps, first of all, we need to increase the local dust-to-gas ratio somewhere in the disk because of radial drift of dust. So somehow in some regions, the local dust-to-gas ratio can increase and exceed unity. And then the streaming instability, the Kelvin-Helmholtz instability, can create these self-gravitating clumps that I showed to you before and form some planetesimals. But of course, if you concentrate dust somewhere, because you have just a given budget of dust, you must decrease the dust density somewhere else, right? And so the dust to gas ratio becomes even smaller elsewhere. So this means that early on, when you have your full budget of gas, you cannot form planetesimals everywhere. You can only form planetesimals in selected sites where radial drift of dust piled up the dust locally somewhere in rings. This can happen at the snow line, at the silicate line. There are different models and that don't always agree with each other. But I think every model has this in common, that the early planetesimals can only form at selective sites, maybe 1, maybe 2, maybe 3. This is model dependent, but only selective sites. Elsewhere, the dust to gas ratio is too little. You cannot form planetesimals by the streaming instability because their density ratio is too small. What can happen, though, is that if this dust is preserved, maybe in structures, in rings, like we observe in extrasolar protoplanetary disk, later at the time when gas is removed, then you can exceed this famous dust to gas ratio 1 everywhere, and then you can have a late formation of planetesimals everywhere else in the disk. And if you think about that, given what we've seen before with meteorites, the fact that we have differentiated meteorites and a differentiated meteorite, so early forming planetesimals, late forming planetesimals, I even hinted at the possibility of a gap between the formation time of the early planetesimals and late planetesimals. This perfectly matches with this view, right? Early on, you can form some planetesimals very quickly, but only at some selective sites where dust could collect. And then you cannot do anything else. You form planetesimals there, elsewhere the dust to gas ratio is too low. You have to wait until the gas starts to leave. And then finally you can form planetesimals everywhere else. But this is by construction late, right? And so this by construction would form undifferentiated planetesimals like the parent bodies of chondrites. Okay, so this is about the formation of planetesimals from dust. And now that we have planetesimals, we have to start to form protoplanets. And there are 2 ways to do it. Planetesimals can collide with each other. Now they have some significant size, 100 kilometers, so some gravity. And if they collide with each other at velocity not too high, their common gravity can stick the 2 planetesimals together, and then we can have the growth of a bigger object by planetesimal collision. On the other hand, these growing planetesimals or protoplanets are still embedded in a disk of gas and dust. So they can also keep accreting dust particles, pebbles particles individually, as these particles drift in the disk towards the sun. And like here, and this is called the process of pebble accretion. So now I will discuss a little.
Sorry, we don't hear any voice.
When? You hear me?
Yes, now it's okay.
What did you miss? What did you miss?
Just 1 minute, about 1 minute.
So did I comment this slide or not? Did you hear the comment of this slide or not?
Partly.
Okay.
Yes.
This you.
Yes, this we heard.
Okay. Yes. So now we go to the second part, where we try to understand how we can go from planetesimals to planets. And there are 2 ways to do it. One is that planetesimals collide with each other, like indicated in this scheme. Planetesimals now have some size, 100 kilometers in size, so they have some gravity. If they collide at low velocity, they come together, their gravity keeps them together, so they grow. And this is called planetesimal growth. The other possibility is that some planetesimals, once it becomes big enough, also they are still embedded in a disk of gas and particles, dust and pebbles drifting radially towards the sun. And they can also accrete these particles one by one as they pass through their orbits and grow by accreting small particles rather than planetesimals. And this is called pebble accretion. And so now I will discuss both processes, planetesimal accretion and pebble accretion, and show which one should dominate in which part of the disk. So planetesimal accretion is the most studied process. And since the year 2000, for instance, this plot is taken from Kokubo and Ida 2000, the first sophisticated simulation of the process. So we see a piece of the disk around 1 AU, and each dot is a planetesimal. Initially, all planetesimal are the same size, but planetesimal can collide with each other and stick. And as soon as the planetesimals stick, they grow, they have a bigger gravity, they attract more planetesimals, so they grow bigger. And as you can see, so there are a number of protoplanets that form in the disk. These are these bigger objects, black dots, that are bigger than 2 times 10 to the 25 grams. And they grow in size. You see, they become bigger and bigger. They tend also sometimes to grow in number. This horizontal line is a line that is wide 5 Hill radii, here radius being the sort of sphere of the gravitational influence of each protoplanet. And protoplanet, to be stable, have to be separated by more than 5 Hill radii. So when these bars overlap, embryos, protoplanets can merge with each other with a giant impact. So for instance, they are less numerous here than here because some merge together. And this is the way protoplanets can grow. On the right, you can see the size distribution of the population. Initially, you have a continuous planetesimal size distribution. And towards the end, you see you have some protoplanets that start growing in mass and reach 1,000 times the initial mass and keep growing. So this is the process of planetesimal accretion. And of course, depends on how many planetesimals you have, right? If you have few planetesimals, don't grow very much. If you have a lot of planetesimals, you can grow very massive and pretty quickly. On the other hand, this growth is not indefinite, because when a planet becomes too massive, it tends to disperse the planetesimals, right? And the capability of a planet to disperse a planetesimal depends on its gravity, which is parameterized by its escape speed at the surface. So a significant parameter is called the Safronov number, which is squared, is the ratio between the escape speed from the surface of the planet that is forming over the escape speed from the star at the orbital distance where the planet is. Okay. So if this ratio is bigger than unity, it means that the escape speed from the planet is larger than the escape speed from the sun where the planet is. When the planet encounters planetesimals, it tends to give an orbital, a velocity dispersion that is of the order of its escape speed. And of course, if this velocity dispersion is larger than the escape speed from the star, then what does it mean? That the planet ejects material from the planetary system. Whereas if the Safronov number is less than 1, when you have an encounter, the planetesimal will get some velocity relative to the planet, but not enough to escape from the star. And so you will have another encounter with the planet, and the next encounter can be more lucky and can lead to an accretion. So accretion of planetesimals is effective only as long as the Safronov number is less than 1. And when the Safronov number becomes larger than 1, the planet tends to waste planetesimals and eject them rather than accrete them. So the rule of thumb is not a threshold, but the rule of thumb is that if the Safronov number is bigger than 1, your planet has too large mass compared to where it is. And so it tends to scatter planetesimal away, eject planetesimal away rather than accreting them. And if the Safronov number is less than 1, then the planet tends to accrete the planetesimals. And so the Safronov number depends on the mass of the growing planet, but also depends on the distance from the star. So close to the star, R is small, so the Safronov number is small. So close to the star, it's really easy to grow by accreting planetesimals. And basically, if you have a disk, a ring of planetesimals at 1 AU, it will form terrestrial planets, and all the mass of the planetesimals will go in the planets. There is very little mass waste. But at Jupiter distance, R is much bigger, and so the Safronov number tends to be bigger. And as soon as the planet reaches a few Earth masses, the Safronov number turns bigger than 1, and then planetesimals are not accreted anymore. They are dispersed. And this is what is summarized here. So in the inner part of the disk, eventually most of the planetesimals are accreted into a few planets. In the outer disk, you can put as many planetesimals as you want with a huge density of planetesimal population. You will start to grow a planet, but as soon as this planet will be massive enough to turn the Safronov number bigger than 1, planetesimal will be mostly dispersed rather than accreted. And for instance, at 5 AU, this happens because the escape speed from the sun is only 19 kilometers per second. That's the escape speed at the surface of an icy planet of 5 Earth mass. So you cannot grow too much. So this is why planetesimal accretion is a valid model to form terrestrial planets, but is a model that has difficulty in explaining the formations of the cores of the giant planets that have to form very quickly in order to be able to accrete the gas before the gas is removed. And for that reason, this process of pebble accretion has been proposed. So how does pebble accretion work? So pebble accretion, as I said, is the accretion of dust and pebbles one by one as they drift through the disk. It has two advantages with respect to the planetesimal accretion. One, that you don't have the so-called isolation problem. So for a planet growing from planetesimals, once you have captured all the planetesimals that are within your reach, well, you cannot accrete anymore because you have accreted everything that you could attract. But pebbles or dust drift through the disk. So even if you accrete everything close to the planet, new material comes in. And the other advantage is that it's easier to accrete a dust particle than a planetesimal because of the friction with the gas. So this is shown in this movie. So here you have a protoplanet that wants to accrete. Misplaced the label and the arrow, I apologize. And here are two particles coming in and encountering the protoplanet. One is a dust particle, a pebble, which undergoes gas drag. And one is a planetesimal, so say 100-kilometer body, for which gas drag is negligible. So the two bodies come in with the same impact parameter, the same relative speed, but as you can see, the fate is different. The planetesimal orbit is just deflected, but not captured. And the dust, because of the gas drag, as soon as it's deflected, the friction with the gas increases, and so the dust spirals and falls onto the planet. So then you have accretion of dust and not of a planetesimal. So this is the process of pebble accretion. So, and the advantage is that, yeah, you have no isolation and an accretion cross-section, which is bigger for dust than for planetesimals. Then, of course, the efficiency of pebble accretion depends on how many pebbles you have. Right? If you have a continuous massive flux of pebbles, can be a very effective process. If you don't have a massive flux of pebbles, of course, it's not a very efficient process. You also need that pebbles are quite big and sediment well towards the midplane so that they are near the midplane. Otherwise, they are dispersed vertically and the protoplanet can accrete them much less efficiently. And so if all conditions are there, so you have pebbles big enough and a big flux of pebbles, it has been shown that indeed you can form the cores of the giant planets in a few million years. But of course, you need to have enough flux of pebbles and they have to be big enough. So pebble accretion by itself is not a universal solution. It depends on the characteristics of the pebbles that you have and the flux of pebbles that you have. So let's go back to the structure of the solar system. In the structure of the solar system, we have these two categories of planets, terrestrial and giants, that are very different in terms of composition, right? So to form the giant planets, we need to capture the gas before that it goes away. So before a few million years. So we need to form cores of multiple Earth masses within a few million years. In the terrestrial planet region, at most we form the Earth, And we have seen that Earth formed in tens of millions of years. Within the lifetime of the disk, only Mars formed. So we have evidence that the solar system produced Mars mass planets in 5 million years in the inner disk, and 10 Earth mass cores in the outer disk in the same time scale. So a factor of 100 in mass, 10 Earth masses versus mass, so factor of 100 in mass. And the orbital period are 10 times lower at Jupiter than at Earth. So it's a 3 orders of magnitude contrast if you factorize the orbital period. So clearly, this suggests that there is not a unique process that formed all the planets, but you must have a process that dominated the formation of the cores of the giant planets working on its own time scale, and a process forming the proto-terrestrial planets working on its own time scale. And I think this is really the signature that pebble accretion is effective in the outer disk and very ineffective in the inner disk. And how do we understand that? We understand that by the size of the pebbles. As I said at the beginning of the lecture, ice is more sticky. So in the disk, we have a gradient of temperature. The disk is warm, close to the star, and cold, far from the star. Close to the star, only the refractory material like silicates can condense. Far from the star, beyond the line that we call the snow line, also ice can condense. So in the cold part of the disk, you can imagine that your grains, your aggregates, your pebbles are a mixture of icy grains and silicate grains all together, centimeter size, maybe decimeter size. This is a reasonable size. It leads a lot of sedimentation on the midplane. And so pebble accretion is very efficient. But when these structures drift towards the sun and pass through the snow line, of course, the ice sublimates. This removes half of the mass. But most importantly, it releases back into nature the silicate grains, which are much smaller because silicates are much less sticky. And so instead of having centimeter, decimeter pebbles, we have sub-millimeter pebbles in the warm part of the disk, which means that this dust is much less settled on the midplane. It's much smaller, much more difficult to accrete. And so, for instance, as an example, if you put here 2 protoplanets, initially half the moon mass, one beyond the snow line and one within the snow line, and then you see how these bodies grow by pebble accretion. You see that the red body beyond the snow line can reach 20 Earth masses in less than 2 million years, and the time when the green body just reaches the mass of Mars in the same time scale. And they see the same flux of material. Well, the green guy sees half the mass flux because the ice goes away, but it's only half. At the end, the contrast is 200. So this is really due to the different size of pebbles and the different sedimentation on the midplane. And shows so that pebble accretion is extremely efficient in the outer disk and can really explain the cores of the giant planets, tens of Earth masses forming within the lifetime of the disk. And in the inner system, they can maybe explain Mars, maybe not even. But in the other hand, in the inner solar system, because the Safronov number is so small, it's so easy to grow the planets by collisions of planetesimals, even once the gas has been removed. But this, of course, takes time, and indeed the Earth forms on tens of millions of years, as we have seen from the chronological constraints at the beginning of the lecture. And in addition, I stopped my simulation when the cores reach 20 Earth masses, because when a planet reaches such a mass, it blocks the drift of dust. And this is because when a planet reaches 20 Earth masses at least, it starts to carve a gap in the disk. So what we see here is the result of a hydrodynamical simulation highlighting the gas distribution due to the presence of a planet. So this is the radial direction. So the sun is in this direction, and this is the azimuthal direction. We are on the midplane, and the colors show the density of the gas. So you see there is a shallow gap along the orbit of the planet, a spiral density wave launched by the planet, and a bump in gas density here at the border of the gap. And because of this perturbation in gas density, the pressure gradients change. And so also the orbital velocity of the gas change. Away from the planet, the orbital velocity of the gas that you see here, the orbital velocity of the gas normalized to the local Keplerian velocity as a function of distance from the sun, the same scale as here. So far away from the planet, away beyond or way within the planet, the gas is sub-Keplerian. As I said before, because it's pressure supported, so dust has to drift in because it's slowed by the gas. But when we approach the gas, the gap, the planet, you can see that the orbital velocity of the gas is strongly perturbed. And in particular here, close to this overdensity of gas, the orbital velocity of the gas can become super Keplerian. Of course, if the planet is 20 Earth mass, it's just barely super Keplerian, but if the planet is 30 or 50, it's more and more super Keplerian. What does it mean? That if you have a dust particle out there, then of course it feels a sub-Keplerian disk, so the particle is slowed down. So it will drift in, but will drift in only where the orbital velocity of the gas turns from sub-Keplerian to super-Keplerian. In this 50 Earth mass case, it's here. Because then the particle would feel a tailwind pushing the particle out. So the particles accumulate here, don't go through. Okay, this is called the barrier. Okay. And it's true for ground dust that is bigger, say, than 100 microns. So millimeters dust, centimeter dust, it remains confined beyond the planet and does not go inside. So that means that as soon as Jupiter became bigger than 20 Earth masses, this flux of material from the outer disk into the inner disk ended. So in addition for pebble accretion to be inefficient in the inner part of the disk, there were no pebbles to accrete from because the flux of dust was blocked, and so there is nothing to accrete. So we envision that as soon as giant planets form, a disk takes this kind of structure. So the dust remains confined beyond the orbit of the giant planet and cannot continuously refill the inner disk. In the inner disk, you have only the dust that remains there from the beginning or is regenerated in collisions from planetesimals, but it's not resupplied by the flux of dust because the flux of dust is stopped at the pressure bump. And so we see a dust cavity. And this is indeed what we see in some extrasolar disks like PDS 70. So we see what is called a transitional disk where the dust is confined in the outer disk and does not penetrate into the inner disk because there is a planet there. And this planet is opening a gap and blocking the dust at the edge of the gap, exactly as I proposed before. So we think the solar system became a transition disk as soon as Jupiter started to form and exceeded 20 Earth masses. And the growth of proto-Jupiter, is the key to understand the separation of distinct reservoirs in the solar system that I will show in a second. The material that forms object in the inner solar system and the material that forms object in the outer solar system are distinct, and so that means that the materials could not mix. All right, so let's speak a little bit about that in particular. So this, which brings me to discuss the topic of the isotopic dichotomy of meteorites. So as I said, meteorites come from asteroids. We have two kinds of we have two kinds of asteroids: carbonaceous asteroids, carbonaceous meteorites, and non-carbonaceous meteorites. And you can look at their isotopic properties. So here we are looking at isotopic ratios of stable ratios of isotopes of the same elements, which are stable, so they don't decay over time. And this ratio, these different isotopes are produced in nucleosynthesis, so due to stellar irradiation, supernova explosion, and so on. And so these are called the nucleosynthetic anomalies. So if you have an object that accretes material with isotopic ratio different than another object, it means that these objects accreted material that comes from different stellar environments, each of which produced isotopes with a given ratio and a given signature. These isotope ratios are expressed in this epsilon notation. So what does it mean? For instance, for titanium, epsilon 50 titanium is the ratio that you between the number of atoms of titanium that have an atomic weight of 50 versus the number of atoms of titanium that have an atomic weight of 47 in your meteorite, normalized to the same ratio in your standard, which is typically Nerf rock, -1 multiplied by 10,000. So it's a deviation with respect to the Earth in isotopic ratio in part in 10,000. And the same for chromium, and the same for molybdenum. And when you see a mu, instead of being a part in 10,000, it's a part in a million. Okay, it's the same concept. And what you see is this isotopic dichotomy. The carbonaceous meteorites and the non-carbonaceous meteorites form two distinct groups with a gap in between. So that's what it means, dichotomy. You don't have a continuum. Okay. Now, if you look at some isotopes like this, you see that the non-carbonaceous meteorites, including Mars and Earth, seem to show a trend point to the carbonaceous meteorites. So some people said, haha, this is a signature of pebble accretion. So initially, all the material had these isotopic properties. Then by accreting carbonaceous material drifting from the outer disk, more and more, the objects acquire properties more and more similar to carbonaceous material coming from the outer disk. We know carbonaceous chondrites come more from the giant planet region because they have a lot of water alteration, so they should have formed beyond the snow line at least. And so this material, these objects form further from the sun than these objects. So this would be the signature of pebble accretion. But if you change of elements, then these trends change. And you don't see a trend pointing towards carbonaceous chondrite anymore. For neodyme, for instance, you see the same trend, but it points the other way around. So here you have a trend from Earth to astatite chondrites, from ordinary chondrites to Mars to astatite chondrites to Earth, carbonaceous chondrites. And here is the opposite of ordinary chondrites, Mars, astatite chondrites, Earth, away from carbonaceous chondrites. So the same trend reversed. If you look at titanium versus, what is this, zircon, you see that the non-carbonaceous meteorites point away from the carbonaceous chondrites. If you look at molybdenum, you see that the non-carbonaceous meteorites and the carbonaceous meteorites form two parallel lines that don't intersect. So this just does not show that the non-carbonaceous material accreted carbonaceous material. On the contrary, one can, so you can use this dichotomy to constrain the amount of carbonaceous material, for instance, that the terrestrial planets accreted. And this can be done, so let's use the same plots. And so using all these plots together, not just this, but this one, but all together, you can demonstrate that Earth accreted at most 5% of its mass from carbonaceous material. So this is again another strong evidence against pebble accretion for terrestrial planets, because if terrestrial planets had formed mostly by pebble accretion, most of the material accreted by Earth would come from the outer disk and would share the same isotopic properties of carbonaceous chondrites, which is not the case. Only 5% of the material comes from carbonaceous chondrites. So the Earth accreted from local material. You can see from all these plots that Earth is always an end member in the distribution of non-carbonaceous material. So there must have been somewhere a reservoir of material, non-carbonaceous in nature, but a little bit displaced, placed beyond the properties of the Earth, somewhere there, you see, in all isotope pairs, from which the Earth accreted as well to have the Earth. So if you cannot form the Earth just by accreting known meteorites, because the Earth is an end member. So for instance, you take this plot, you can take all the known non-carbonaceous meteorites that you want, all the known carbonaceous meteorites that you want, you combine them together, you will always be somewhere here, and the Earth is there. So you must have an end member somewhere else, which is not collected in the meteorite collections today. Possibly because this reservoir of material was close enough to the sun, and none of these objects have ever been captured in the asteroid belt. Or maybe because the collection of meteorites we have from the asteroid belt is very biased, and we don't sample all asteroids. And so there is some reservoir out there that we don't sample. This is what the Earth shows from its isotopes, which is, I think, is very interesting. So leaving pebble accretion beside that as an important process, because as I said, there is too little material coming from the outer solar system accreted in Mars and the Earth. It's unlikely that the terrestrial planets accreted by pebble accretion because they would form too quickly. Pebble accretion works only as long as you have the gas. So first, they would violate the afternoon tungsten chronological constraint for the Earth. And second, they would start to migrate because when you form planets in a disk, they start to migrate if they are massive enough. And this would move Earth and Venus towards the sun, leaving Mars behind, but Mars is not left behind. The separation between Mercury, Earth, Venus, Earth, and Mars is a regular one, so there is no sign of migration of Earth and Venus relative to Mercury and Mars. So I think everything points against pebble accretion for the terrestrial planets. And so for the terrestrial planets, the classic model of accreting planetesimals is much more appealing, and it's not problematic because the Safronov number is so small, so it's very easy to grow by accreting planetesimals. So this model has been proposed originally by George Wedderly, and it's now supported by all kinds of simulations that have been done. So if you start from a disk of planetesimals, you form by planetesimal collisions, you form embryos, planetary embryos of about the mass of Mars. This shows results from a recent paper that, yes, it's quoted down there, Walsh and Levison. So what you see here is the population of planetesimals in colored dots and a population of protoplanets in black dots at 3 snapshots in time as a function of distance from the sun. So you see quickly you have protoplanets that form in the inner disk, and then this protoplanet start to form further and further away from the sun. Their mass typically stalls around the mass of Mars. That's perfect because we know that Mars forms in a few million years, but not the Earth. That takes much longer. So in on the lifetime of the disk, a few million years, you form protoplanets the mass of Mars. Then the gas goes away, and then the system is there. It's not stable, too many planets. And so these objects what can they do? They can just collide with each other. The Safronov number is small, so they will collide. So this animation shows a simulation taken from to O'Brien et al. 2006. So we have these protoplanets here in red, and they are in the gas has gone away. Protoplanets are in red. The planetesimals are in green. These dashed lines show the boundaries of the asteroid belt. Jupiter is fully formed. This is the orbital eccentricity. The time is showed at the top. So let's run the movie. And you see that because of the perturbations from Jupiter, embryos and most of the planetesimals tend to leave from the asteroid belt, but the embryos collide in the inner disk, in the inner part, where the Safronov number is really small, growing planets. And on a time scale of a few tens of millions of years, you can grow a handful of terrestrial planets, 2, 3, 4, here in this case 3, which have masses comparable to the mass of the Earth on a time scale consistent with the afternoon tungsten chronology of the Earth. So we have Mars rapid formation in the disk of gas and planetesimal, Earth formation on a time scale of tens of millions of years. In the terrestrial planet zone, no formation of planets in the asteroid belt. That's pretty good. That's pretty perfect. And indeed, so this model explains a lot of what we know for the Earth. So we form a few terrestrial planets in the terrestrial planet zone, no planets formed in the asteroid belt in most of the simulations. The most massive planets are typically of Earth mass. The orbits have good orbital eccentricities and inclination. The time scale is tens of millions of years to form the Earth is consistent with chronometers. There are several giant impacts, so formation of the moon is not an oddity. Even they can get some planetesimals from the farther distant asteroid belt, which can bring waters and that are volatiles in good proportion. The problem of this model is that typically the planet formed at the distance of Mars is too big. These are the real masses and positions of the terrestrial planets, Mercury, Venus, Earth, and Mars. And this is what is produced by simulations like the one I just showed. So as you can see, Earth and Venus are well reproduced. You can even see a trend toward forming a small Mercury, but the planet formed at the location of Mars is typically way too massive and comparable to Earth. And Mars mass objects when they form are formed in the asteroid belt, which is not correct. So it has been shown that in order to form a small Mars, we cannot start from such an extended distribution of planetary embryos and planetesimals. We need to start more from a ring. And if we start from a ring, then with an inner edge and an outer edge at about 0.71 AU, then indeed the simulations reproduce the mass distribution of the terrestrial planets as first shown by Brad Hansen, 2009. So again, these are the real terrestrial planets. The open dots are the masses of planets produced in simulations that start from a ring rather than the disk of planetesimals and embryos. Now, the question is why a ring? But I think I showed to you before that the first planetesimals necessarily form in a ring. So the formation of a ring of planetesimals and hence of planetary embryos is a natural consequence of how planetesimals form in the streaming instability. Before we understood this, people looked, including ourselves, at more ad hoc scenarios invoking the migration of Jupiter, what is called the Grand Tack, and all more other exotic scenarios. But now that we know that the first generation of planetesimals necessarily has to form in a ring, I think there is not much of a surprise that the mass distribution of the terrestrial planets reflects the initial distribution of in a ring. So the planetesimals formed a massive ring near 1AU. The asteroid belt probably never contained much mass. And so as a consequence, this mass distribution of terrestrial planets came out. What about the giant planets? So the core, as I told you, they form probably by pebble accretion, no problem. Then you have to accrete the envelope. But once you have a core that is 10 Earth masses or more, then the core starts to accrete the gas. This was studied already quite a while back by Pollack et al. Forgot to put the reference here. Pollack et al. Is a very seminal paper. So it shows, so this in black is the build-up of the core, which was prescribed there, but we know the core can form pretty quickly by pebble accretion, and then it stalls because pebbles start to be stopped at the edge of the gap. When the core reaches 10 Earth masses or so, there is some gas that starts to be accreted. So the amount of gas that is accreted around the planet is shown by the dotted curve, and the dashed curve is the sum of the dotted plus the solid. So the total mass of the planet, solid core plus atmosphere. So the atmosphere builds up, and then when the atmosphere has the same mass as the rocky or the solid core, you see a sharp transition where you start to have an exponential growth, an exponential runaway accretion of gas. And this is because now most of the mass is due to the atmosphere. And so the more gas you accrete on the atmosphere, the more massive the planet is. And so the more capable it is to capture gas from the disk, and so forth. Until the atmosphere is a fraction of the total mass of the planet, well, the ability of the planet to capture gas is due mostly to the mass of its core. But when most of the mass is in the atmosphere, then the more massive is the atmosphere, the more capable is the planet to attract gas, and so build an even more massive atmosphere. So you have this runaway growth of the planet that brings the planet into the category of a gas giant of hundreds of Earth masses like Saturn and Jupiter. And this is at the end only limited by the flux of gas towards the giant planet and ultimately the lifetime of the disk. So the common interpretation is that Jupiter and Saturn started to form early enough to be able to capture these hundreds of Earth masses of gas before the disk disappeared, whereas Uranus and Neptune got caught in the action, and they were starting they were still in this phase with a total mass of about 15 Earth masses, most of the mass still in the core, fraction of the mass in the atmosphere, when the gas disappeared. And this is because their core grew more slowly, and then there was less time for the accretion of gas. When we talk about planets so massive in the disk, and so this would be true also for the Earth, if the Earth formed quickly enough by pebble accretion, then we have to worry about migration. So when planets form and become massive enough, they perturb the disk, And as we see in this animation, so what we see here, okay, so let's stop the animation. So this, it's an hydrodynamical animation. The sun is at the center. The colors show the density of the gas. We put a planet here. And the planet modifies the gas by its gravity and perturbs the density of the gas. So there is a concentration of gas around the planet. That's also where the planet is drafting its atmosphere. And then you see a spiral density wave where the gas has a high density that is ahead of the planet in the inner part and trails the planet in the outer part. And because of this spiral density wave, the gas exerts some forces on the planet that slow down the planet. And so the planet orbit has to shrink. And what we see in this animation is the evolution of the planet in a co-rotating orbital frame. So we don't see the planet rotate around the sun because otherwise you become hypnotized. So the planet is always here in azimuth, but you see just its radial motion towards the star. And here you see the projection of this radial motion. So the track, the migration track as a function of time in orbits. Okay. So here migration just started. Now you can see migration in action. So you see the planet is migrating, so its orbital radius is shrinking. But in this simulation, the planet is also growing in mass because it's capturing gas. And when its mass becomes big enough, as here, you see the planet opens a gap of gas around its orbit, what I started to show before. That's why the dust stops at the outer edge of the gap. And so you have a transition from one migration mode to the other migration mode, because the planet now is in the gap and has to move with its gap, which slows down the migration considerably. So initially the planet accelerates as it grows, but then when it opens a gap, migration slows down, and you see the profile of the migration as a function of time. It is significantly slow. So this is the process of planet migration. We call this type 1 migration before opening of the gap, type 2 migration after the opening of the gap. Type 1 migration is faster than type 2, and type 1 migration is actually, the speed is linear in the mass of the planet, and type 2 is lower and independent more or less on the mass of the planet. Okay, so we need to worry about migration of planets, and so question that we need to address is why our giant planets are so far out if they should have migrated in. And indeed, when we look at extrasolar giant planets, we find them typically at around 1-2 orbit astronomical units rather than 5 or 10. And we find even some hot Jupiters very close to the central star. So some people have proposed that this is because our giant planets were very far out in the Kuiper belt and migrated in, and then the disk disappeared. But this raises a number of problems in the structure of the Kuiper belt, in the structure of the asteroid belt. And also, we've seen before that the snow line is the best place to form planetesimals, to accrete pebbles and so on. And if all the planets form in the Kuiper belt, what for the snow line? So this is something I really don't like. I prefer the idea that Jupiter started to form at the snow line and grew maybe really quickly. So it started opening a gap really quickly, which slowed down the migration. And in the case of the solar system, in addition, we have a particular role played by Saturn. So the coexistence of Saturn and Jupiter suppresses migration. This is seen in all numerical hydrodynamical simulation. Like this one, for instance, we have Jupiter and Saturn forming further out in the disk. Jupiter migrates towards the star, the sun. This is the distance from the sun as a function of time. Saturn migrates at the beginning faster because it does not open its gap. Eventually, Saturn is trapped in a resonance, the 3-2 resonance with Jupiter. And you can see that as soon as Saturn is trapped in resonance with Jupiter, the migration of Jupiter stops, actually reverses a little bit. And this is for a warm disk, which is relatively thick. If you put a cold disk, the migration is clearly reversed. So, but what is important for us is that Jupiter stops approaching the sun. So I think this is really the key to understand the structure of the solar system. This gravitational game by Jupiter and Saturn that stops their migration. At that point, everything follows, right? So we can see here a simulation where we inject Jupiter and Saturn just beyond the snow line, so they don't migrate because of this gravitational interaction. Beyond them, we put a number of super Earths. The color here shows the mass of these objects, about 3 Earth masses. We are still in the disk of gas. And what do we see? We see that so Jupiter and Saturn don't migrate, but the other planets want to migrate, but they are blocked by the presence of Jupiter and Saturn, and they go in resonance with Jupiter and Saturn, and where they cluster, and so they tend to collide with each other to form bigger planets. And if we are patient enough, then we see that these 4 planets eventually will merge. And in a second, and we see this will form a little bit of time. This will form 2 planets with about 15 Earth masses, so completely analog of Uranus and Neptune. Okay? And no giant planet goes through the inner disk. So this region of the disk with its initial planetesimals, planetary embryo, remains protected, unperturbed. And so at the disappearance of the disk, the planets can keep growing in the inner part and form the terrestrial planets on a longer time scale. This model for the formation of Uranus and Neptune, I think, has the merit to explain why the spin axes of Uranus and Neptune are so inclined with respect to the orbit. Neptune's spin axis is inclined by 30 degrees and Uranus even by 98 degrees. In principle, planets should form with a spin which is orthogonal to the orbital plane. In particular, they form by pebble accretion. And but this is not what we see in Uranus and Neptune. It's also not what we see in Saturn, but Saturn is in a spin orbit resonance that tilted the planet. So we can understand the tilt of Saturn, but not the tilt of Uranus and Neptune. The only explanation for the tilts of Uranus and Neptune is that they suffer giant impacts with other planets of several Earth masses in mass. And the kind of assemblage that I showed you with super Earths collecting in resonance, colliding with each other until their number decreases and their mass increases, exactly produces these giant impacts that tilt the planets. And so at the end, we should expect a random spin obliquities for this Uranus and Neptune, and so explaining what we observe. Of course, what we have at the end is due to Jupiter, Saturn, Uranus, and Neptune, but the orbits are not right? The system is compact. The planets are between 5 and 15 AU, and they are all in resonance with each other. The orbital periods are in resonance. Saturn is in the 3-2 resonance with Jupiter. For instance, Uranus here in the 4-3 resonance with Saturn. Neptune is in the 5-4 resonance with Uranus. We have a resonant chain. And this is, of course, not what we see today. So these are the orbits that we found in the previous simulation, but the orbits today are much more separated, and Saturn is not in the 3-2 resonance with Jupiter, is almost in the 5-2, so it's almost at 10 AU. Uranus is at 20 AU, Neptune is at 30 AU, and totally different from the orbits that we got in these migration simulations. So what does it mean? That either these migration simulations are wrong, but we don't see how, because migration is really a fact, and everybody finds this kind of final configurations, or after the gas removal, there must be a process that is able to transform the orbits of the giant planets and moving the planets from these initial orbits to their current one. And we think that this is what happens during an instability. So this is the key of what is called the NIS model. So in the current version of the NIS model, we put the planets where the hydrodynamical simulations of planet migration put them. So there is no arbitrary choice in the initial conditions of the planets. We remove the gas and we only assume that beyond Neptune, there is a belt of bodies, the ancestor of the Kuiper belt, with a total mass of about 20 Earth masses. And that's it. And then we let the simulations, the interactions work, and the interactions among the planets and with the planetesimal disk destabilize the orbits of the planets after a while. And this while depends on this gap. If the gap is large enough, this happens after a lot of time. So this gives me time to speak about. But if the gap is narrow, the instability occurs much earlier. And when the instability occurs, which is now, then the planets break out of their resonant chain. Their close encounter, mutual close encounters separate the orbits. Uranus and Neptune are thrown into the primordial Kuiper belt, dispersing it. The dispersal of the primordial Kuiper belt damps the inclination and eccentricity of the orbit of Uranus and Neptune and park them in 20 and 30 AU. And Jupiter and Saturn separate and acquire a partially excited orbit, comparable actually to really what we observe today. And not only we can reproduce the orbits of the giant planets, not in all simulations, just a fraction of the simulations, but that's enough. But also the dispersal of this disk, I don't have time to show it, but is capable to reproduce what we observe in the Kuiper belt, the scatter disk, the Oort cloud. Some objects are captured as Trojans of Jupiter and Neptune. Some objects are captured as irregular satellites of all the giant planets. So really, through an instability, post-gas instability, we are able to reconstruct the entire structure of the outer solar system. And this is why it's considered today that this post-gas instability is really compelling and occurred in the solar system. And there is a beautiful review paper by David Nesvorny in the annual review series that describes really very in detail how the full solar system took shape during the giant planet instability. Because the lack of time, exactly, I will go to the end. So I think there is no doubt that the giant planet instability happened in the solar system. But what remains an open question is when the instability happened. So a priori we cannot say, because as I said, it depends on this gap between the initial position of Neptune and the initial inner border of the planetesimal disk. And of course we have no knowledge of what that was. If it was narrow, the instability occurred very early. If it was very large, the instability occurred very late. We don't know. So we need to guess when the instability happened from constraints. At the beginning, when the first NIST version of the NIST model came out in 2005, the people working on the moon still believed that the moon underwent a terminal lunar cataclysm. So that all of a sudden, 650 million years after moon formation, the moon bombardment rose up, became much stronger than before. And so we said, well, if this is true, then the giant planet instability, if it occurs at that time, would create a huge spike in the bombardment, because as the giant planet change of orbit, the asteroid belt is destabilized, the Kuiper belt is destabilized, so there is a huge surge in the bombardment of the terrestrial planets and the moon. But the revision of the chronology of lunar samples have shown that this terminal lunar cataclysm was not real, was mostly bias of how shocks have been measured. And so there is really no need for a so late giant planet instability to explain a lunar cataclysm, because lunar cataclysm did not happen. Most likely the moon just experienced a declining bombardment, and there were some inconsistencies with the geochemical record, which we removed. So there is no reason to invoke a very late giant planet instability. And from the dynamical point of view, an earlier instability is much easier than a later instability. The preservation of the binaries in the trans-Neptunian disk, we form all these binaries in the collapse, and we still need to see 50% of them today. This argues, as nicely shown by Nesvorny, that the disk has been dispersed in less than 100 million years. Otherwise, the collisions between planetesimals in the massive precursors of the Kuiper belt would have dissociated the binaries as it has dissociated the binaries in the asteroid belt. So the instability probably occurred in the first 100 million years, but when? Some people propose that it occurred very early, as soon as the gas disappeared, and maybe this explains the small mass of Mars, but I showed you that this is not needed. The fact that planetesimals forming rings explains the small mass of Mars without the need of ad hoc models like the early instability or the Grand Tack. So we don't know when the instability happened. Any date from gas time removal to 100 million years is currently acceptable. So we'll end here and take your questions with a few take-home messages. So of the various steps of solar system formation and evolution, the last one is the one we are most confident of. The giant planet became unstable, and this changed their orbits from the original resonant chain acquired during migration to recurrent orbital distribution, and the entire outer solar system took shape during this instability, although I did not have time to show how. When this happened is not known, as I just said. Then as we go backwards in time, things becomes more confused and less constraints. And the fundamental process of planetesimal formation, I think it's partially understood. In the sense it's clear that planetesimal has to form from self-gravitating clump of dust and pebbles. It's still not clear how and where planetesimal formed, in one ring, in two rings, in three rings, how the dust was preserved in the disk to be available for the formation of chondrites, and so on. So there is the actual radial extent of the planetesimal disk. So there is a number of questions that remain open on the original mass distribution of planetesimals. The origin of chondrules remains mysterious. So chondrules are these little sub-millimeter spherules that make the chondrites, but these chondrules have been heated after millions of years at temperatures over 1,000 degrees. And how this heating event occurred is not understood, and how these chondrule precursors remained in the disk despite they should drift into the sun for so long is not so well understood, and probably there are pressure bumps that capture these particles, but in how many sites, how many rings, it's not clear. The question of migration of giant planets in the gas is not fully understood. It's related to the question of where did the cores of the giant planets start to form. So I think the snow line is the place where the core started to form, which means very little migration. And I really think that this argues for a very rapid formation of Jupiter and very rapid formation of Saturn. And then once you have Saturn and Jupiter, migration is avoided. So the confinement of ring of material in a ring of terrestrial planet near the terrestrial planet is still unclear, although probably it's a signature of the formation of the first planetesimal. So clearly there are still outstanding questions on the how planets and planetesimals form and the history of our solar system, and even more so when you start to compare the solar system structure to the structure of extrasolar planetary systems, which are so different. So the diversity of planetary system is another big question that is still largely unsolved. So we'll stop here, and in the last 15 minutes or so, I'm happy to take your questions. Thank you.
Okay, thank you, Alessandro, very much for this extremely interesting lecture. So all students are encouraged now to ask the questions in the chat. So please. So while all students are writing their questions, so let me then start with my questions. So I was really fascinated about this case of aluminum-26 about heating of all celestial bodies. So in this sense, how unique our solar system is. Do we expect the same scene for other solar systems or not?
No, you're right. We expect a big variability depending on the environment where stars form. So these radioactive elements tend to disappear relatively quickly. So they are produced in evolved stars, either supernovae or massive stars that evolve as Wolf-Rayet. In the case of our solar system, we tend to exclude synthesis in a supernova, because supernova should produce not only aluminum-26 but a lot of iron-60. And we see so the signature of the presence of aluminum-26 in CIs, but not the signature of iron-60. So it's expected now, the consensus is that the aluminum-26 that we see in the solar system was produced in one or a few massive stars that evolved as a Wolf-Rayet in the stellar association in which the sun formed, which means that the sun is not one of the first stars that form in the stellar association. So there is a lot of contingency there. And so some stars may form completely deprived or short-lived radionuclei. Other can have even more. Other could be affected by supernova explosion and have, in addition to aluminum-26, also iron-60. So melt even more easily planetesimals that form even further later in time. So I think, yeah, we have to expect a large variability. There are observations, I think, in gamma ray that make maps of aluminum-26 in the galaxy. So there is a background of aluminum-26, which is clumpy because of this stellar evolution, and clumps with an aluminum-26 content consistent, comparable with what is recorded in CIs are not rare. So I would not say we are an oddity, but we certainly not the typical characteristics.
Okay, thank you. So now let's proceed with the questions from the chat. So the first question: how do close passages of a neighboring star affect planet formation and evolution? What are the implications of galactic distributions of planetary systems?
Yeah, this is a nice question. I did not speak about stellar encounters, but of course, if you this form in a binary system or you have a very close stellar encounter, there are several effects. First of all, if you are still in the phase of a disk, the disk can be truncated, so you have a small protoplanetary disk. If the encounter happens later, it can destabilize the population of planetesimals or planets in the disk. And so clearly affects the final structure of the system. In our solar system, because of the distribution of the planets, of the cold Kuiper belt, which is this component between 40 and 50 U, where planetesimals really preserve the initial small eccentricity, small inclination orbits acquired in the disk. And then the existence of the Oort cloud with an inner Oort cloud down to 1,000 AU suggests that the sun had encounters of stars no closer than 1,000 AU. And presumably was not another solar mass star, but a more typical star with about 1/10 of a solar mass. So we need to avoid closer stellar encounters, otherwise the cold Kuiper belt would be perturbed, and did not. And we need that kind of encounter in order to form the inner Oort cloud. So this transition from the scattered disk to the Oort cloud that starts at about 1,000 AU. So in some sense, we can deduce what the sun experienced. But of course, again, it's one specimen and it's not necessarily the most typical outcome. And so there are models explaining some extrasolar planetary systems with distant planets, eccentric planets, free-floating planets, invoking more closer stellar encounter.
Okay, thank you. So the next question. So, Professor Morbidelli, I would like to thank you for your fascinating talk. I have a particular interest in nanomaterials, and I'm wondering if nanomaterials are being studied in relation to the origin of solar system. Besides carbon, what other elements or materials at the nanoscale would be interesting to consider in these studies?
Yeah, absolutely. So in meteorites, we see what are called pre-solar grains. Pre-solar grains are nanometer particles that have huge isotopic anomalies. So these have been synthesized directly in the envelopes or evolving stars or supernovae and came into the disk and have been incorporated as such in the meteorites. And they are considered to carry the isotopic anomalies that at the end they produce this dichotomy and so on. So most of the interstellar grains, pre-solar grains, have probably been accumulated together. They are nanoparticles. So in order to make you need many of them already to make a micron-sized particles, and many more to make a millimeter-sized particle. So as you clump pre-solar grains together, you tend to average their isotopic properties, and this gives the isotopic properties of the solar system slightly different for the inner system and the outer system. But some nanoparticles can be identified in the matrix of chondrites today, and so they help explaining the genesis of the solar system from materials coming from a variety of stellar environments. It's a very rich field of research.
Okay, thank you. The next question which we have, so not sure, I heard this correctly. Did you mention that the 50% of all planets are formed in binaries? However, none of the planets in the solar system is binary. Is that right?
No. You misunderstood. It's 50% of the planetesimals forming binary. Actually, according to these models of collapse of self-gravitating pebble clumps to form planetesimals, all planetesimals should be born as binaries. And in the cold Kuiper belt, which is the least perturbed structure, 50% of the planetesimals are binaries today. Okay. The others have been dissociated or became contact binaries, like Arrokoth, and visited by New Horizons spacecraft. In the asteroid belt, has been much more perturbed and underwent much more violent collisions. So we don't have any primordial binary left that we know of. And we have asteroids with satellites, but these are collisional products and not the remnant of the original formation. Planets do not form by the collapse of a self-gravitating clump of pebbles in much mass. So they form by the collisions of planetesimals or the accretion of individual pebbles by pebble accretion. So there is no reason that planets form as binaries.
Okay, thank you. So let me also ask a single question. So what are chondrules? Were they really molten drops in the past or not really?
Yes. These are silicate. These spherules are so grains that heated up enough that the olivine melted. And in order for the olivine to melt, every time you have a liquid, that means that you have a high partial pressure of that species, otherwise you just sublimate. And so somehow the grains got clumped together, and now we know how. I showed these clumping processes. And for some reason, some grains got heated up. And we don't know if this is due to lightnings developing in the disk or these clumps crossing a shock wave. It's really, there are several models about how chondrules heated up. And so it heated up, and some silicate evaporated, built this partial pressure. So the silicate started to melt and will remain liquid. And then on a time scale of a few days only, the temperature dropped again, and this liquid recrystallized. And today, so we see these spherules, and these are really recrystallized liquid. We can identify inside of them some relic grains that didn't melt completely at the time of heating. So, but the most of the constituency of the chondrule is this recrystallized molted olivine. So by studying the chondrule, it's pretty clear what happened. What is really not happened is what heated particles so late. Also, we can date chondrules thanks to this melting and recrystallization. We know the chondrules form from 2 to 4 million years after sea ice. So it's late. At that time, the disk is very cold. So we really need a localized event to rise the temperature, and localized enough that the chondrule can go away on a time scale of a day. So it's unclear. So that's why the most accepted scenario is that there is no accepted scenario, first of all. But if people had to vote, most probably would vote for a shock a wave. So you have an overdensity of gas in the shape of a wave. And when the particle enters into this overdensity of gas, it enters at supersonic speed. This creates a shock that hits the particle and can melt and vaporize part, and then it goes through the shock, and behind the shock, the gas is cold again. The shock can be due, it's not the spiral wave launched by Jupiter is not enough. So Steve Dash, for instance, has proposed that when the giant planets formed, some proto-giant planets become destabilized and they acquire, so these are Earth mass protoplanets that become eccentric. We've seen some in my movie forming Uranus and Neptune. And these eccentric objects then are supersonic in the disk, create some bow shocks, and this could form chondrules. There is another model where chondrules are instead the debris in physical collisions of objects. So objects collide, and in the collision, part of the colliding objects are heated up and melted, and so you have droplets of liquid thrown out in space, and then they cool down. This is, for instance, the model of Simon Locke and Sarah Stewart. The problem of this model is how to explain the relic grains that we find in chondrules, and so this model does at some point had the favor of the community, now much less, but it remains a huge problem, open problem, and there is no consensus.
Okay, thank you. So I see our time is running out, and also I don't see any further question in the chat. Okay. So with this, I would like, okay, no one is...
No, this is just a message.
Okay, yeah, thank you. Yeah, there are a lot of thank you message, by the way, in the chat. So thank you, Alessandro, very much again for this interesting, informative lecture.
You're welcome, Sergey.
And yeah.
Okay. Talk to you soon, maybe next year. Okay.
Yes.
Okay.
See you.
See you. Bye-bye.
And have a nice day still. Yeah. Bye-bye.
Bye-bye.